In this video, we're going to look at how sampling distributions behave, particularly with regard to the mean and standard deviation of a sampling distribution. So if you recall, sampling distribution is the distribution of values taken by the statistic, or in other words, X bar, in all possible samples of the same size from the same population. So here I have I've generated a population based off of a normal distribution, and this population has a mean of 5 and a standard deviation of 1. And this population has a lot of individuals in it, and so this graph here, because it represents the population, is made up of all the individuals in the population. Now, in order to create the true sampling distribution, I would have to take all possible samples of the same size from this population. Realistically, that would just be thousands upon thousands upon thousands of samples. So that's not going to be realistic for our case. So what we're going to do instead is look at kind of a simulated sampling distribution. We're not going to take all possible samples, but we're going to take a bunch of samples, like 100 samples. And this should give us kind of a general idea of what the sampling distribution would look like, even though it won't be perfect. So thinking about that, what I did with this data, which I generated in Minitab, is I took a sample of 5 individuals from this population here. I recorded their sample mean of those 5 individuals. Then I threw those 5 individuals back into the mix, and I took another sample of size 5, recorded the mean, threw that back in, took another sample of size 5. And I did this over and over and over again till I had a bunch of different samples. And from each of those samples I had calculated the sample mean, and then I was able to look at the distribution of values of the sample mean that were taken. So this is a histogram of the sample means that I got from, I think it was around 100 samples that I took here. And so this isn't the exact sampling distribution, but it gives us an idea of what the sampling distribution would look like. And so this distribution here is made up of sample means. So we're graphing sample means here, whereas with our population, we're graphing the individuals. So while we're here at the population, just recall that the true mean of the population is 5, and the true standard deviation of the population was 1. So let's look and see what happens to the mean and the standard deviation when we start looking at a sampling distribution. Notice that the mean really close to 5, which was the same as the mean of the population. But what happens to the standard deviation? Well, our population standard deviation was 1, and now we can see that when we have a sample of size 5, the distribution of X bar values for samples of size 5 is 0.4146-ish, which means that it's a bit smaller than the standard deviation of the population. Let's look and see what happens here when we took a sample of size 10. So now instead of taking samples of size 5, I took 10 individuals from that population, measured their mean, threw them back in, took another 10 individuals, measured their mean, threw them back in. I did that lots and lots of times, and here is a histogram of all the sample means. This time these sample means were calculated from samples of size 10. So let's look and see what happened in the mean and standard deviation here. Notice that the mean stayed really close to 5, which was the same as the mean of the population, and the standard deviation got smaller. Okay, so then, I looked at samples of size 5, I looked at samples of size 10, I decided to go all wild and crazy, and I looked at samples of size 30. Same process. So I took samples of 30 individuals from that original population, I measured their mean, threw all of them back in, took another sample of size 30, measured the mean, threw it back in. When I'd done this lots and lots of times, then I made a graph of all those sample means, and that's what you see here. So thinking just about the mean and standard deviation, look at the mean here, really close to 5. So the center of these distributions is staying centered right around mu, the true mean of the population. And the standard deviation is getting smaller and smaller as our sample size increases. So you can kind of look and see how this changes as the sample size changes here, because the scale on the bottom is the same. You can see how it's still staying centered right around 5, but the standard deviation is getting smaller. So as the sample size is increasing, the side effect of this smaller standard deviation with our sampling distribution is that it's making it more likely that we get a sample mean that is closer in to the true value. And the whole purpose of these sample means is to estimate the true value. So we're hoping that our sample mean is going to be close to mu, the true value that we're trying to estimate. All right, so this was for a normal distribution. We started with our population, but normal distributions, they're beautiful, they're symmetric, they're bell-shaped. We love normal distributions. What happens if we start with something that's not a normal distribution? So I went ahead and created a population based on a uniform population. So here, this population has a mean of 0.5 and a standard deviation of 0.28919. And I went through the same process. I looked at taking samples of size 5, samples of size 10, and samples of size 30. And each time I made a graph of that approximate sampling distribution to kind of see how the mean and standard deviation changed as the sample size changed. So again, before I move on, this graph here represents individuals because it is the whole population. Now we're going to look at the sampling distributions. So here's the first one. When I took samples of size 5, so what's represented in our histogram here is sample means when I took samples of size 5. So notice that the mean stayed really close to the mean of the population, really close to 0.5. Standard deviation got smaller. What happens when I took a sample of size 10? Well, mean stayed really close to 0.5, which was the mean of our population. Standard deviation got even smaller. And here's what happened when I took samples of size 30 and calculated the mean from each sample. The mean of all those sample means, the X bar, stayed really close to 0.5. Standard deviation got even smaller. So that's a uniform distribution. Uniform distributions, they're at least symmetric, even though they're not quite as beautiful as normal distributions. I wanted to see what would happen if I started with a really ugly distribution. So I created a population based on the exponential distribution, which, as you can see, is not at all pretty. I mean, it's very skewed, lots of outliers, just all around ugly distribution. And this distribution had a mean close to 1, about 0.98, and a standard deviation also close to 1, about 0.99. So this is the population. I followed the same process. I took samples of size 5 and looked at their means. I took samples of size 10 and looked at their means. And I took samples of size 30 and looked at their means. So starting with the sample size of 5, here's what the approximate sampling distribution looked like. So you can see the mean. We're seeing a pattern here, right? Mean stayed pretty close to what the population value was. Standard deviation got smaller. Then here, samples of size 10, mean stayed pretty close to what the population value was, about 1-ish, 0.98, 0.99. Standard deviation got a little bit smaller. When I took samples of size 30, we see the same pattern. The mean stayed really close to 1, which was the mean of the population, or near 1. And standard deviation got even smaller. So you can see that we're seeing a pattern here. It happens every time. As your sample size increases, the mean of the sampling distribution is going to be equal to the mean of the population. And the standard deviation of the sampling distribution is going to get smaller. So what we've learned from looking at these approximate sampling distributions is that the mean of a sampling distribution is going to be equal to mu, the mean of the population. And the standard deviation of the sampling distribution, we saw that it got smaller and smaller with relation to the sample size. There's an actual mathematical relationship there, and that is the standard deviation of the sampling distribution is equal to sigma divided by square root of n. Remember, sigma is the standard deviation of the population. Check out the next video where we'll talk about the shape of the sampling distribution.